Good afternoon, everybody. Let's start the class for the day. So we are going to talk about correlation today, and then we're going to do hypothesis testing using correlation. Okay. What is correlation? Correlation is the association or relationship between two variables. Okay. Correlation measures the association or relationship between two variables. The value of the exact value of the correlation gives you the level of strength or correlation between these variables. For example, think of number of hours you work. So let's say X is the number of hours you work and Y is the amount of money you make. There is some sort of relationship between these two variables, X and Y. The more hours you work, the more money probably you make, right? So there is a correlation or association between these two variables. One very important thing I kind of want to mention here, particularly is true for medical science and psychology and fields of those nature. People tend to associate correlation with causation. Okay, correlation with causation. What does that mean? So let's say people think, okay, so during the winter, okay, during the winter you get the flu. Typically, during the winter season you get the flu. So sometimes people tend to think that cold weather cause flu. Okay, cold weather causes flu. But as it turns out that cold weather actually doesn't cause you to have flu. It happens to be the case, I heard, I'm not a medical expert, that during the cold season, certain bacteria happens to be more active, and that causes you the flu. So from the surface, if you look at it, oh, okay, it's cold season, so you're getting flu. So you're thinking cold season causes flu. That's called the causality. That means the reason for something, okay, cause or source of something. But just because two variables have correlation does not mean that one causes the other. So that's very important thing. Okay, does not necessarily mean that one causes the other. That's how I put it. Correlation does not necessarily mean causation. So that's important thing to remember. So cold weather does not cause you to have flu, but rather certain bacteria causes you to have flu that happens to be predominant or more common during the cold season. So the bacteria actually, that presence of that bacteria causes you to have flu, not the cold weather itself. Another good example I could think of would be, allergies. Okay, during the spring season or somewhat moderate and warmer weather, during that time you get allergy. You might be thinking, associating spring season with allergy because there is an association or a stronger relationship between these two events. Okay. However, spring season doesn't necessarily cause you to have allergy, but rather pollen that's present during the spring, the pollen in the air that's present during the spring that causes you to have allergy. It creates some sort of allergic reaction in you. I hope this kind of gives you a sense of what I'm talking about. Are you guys okay with it?
Yes.
Okay.
Yeah.
So remember, correlation is the association or relationship between two variables. Of course, I gave you some example in with our ordinary day events, but in mathematics we have to quantify things. You have to associate numbers with things, and then you can measure correlation. The way you measure correlation is by using a formula, and which is this formula. I'll get to that shortly. Now, Some of the variables are very strongly correlated, and some are not so. Like, for instance, if you get paid hourly, if you work 1 hour, you get, let's say, $15 right now. Okay, why? If you work 2 hours, you get $30. It's a linear relationship, right? If you work 3 hours, you get $45, and so on and so forth. The more you work, the more money you make. The more you work, the more money you make. Okay. On the other hand, I could give you a sort of more like a soft example. Think of going to a restaurant. Okay. You go to a restaurant. You spend money, and at the end, when you get the bill, you pay the bill plus you pay what? Tips. So let's say X represents the amount of money you spend. Y represents the amount of tip you gave. Unlike the last example where you got paid hourly, every extra hour you work, you got $15. However, that relationship was very strong relationship. You will see shortly that correlation is 1. Okay, correlation coefficient is denoted by R. So that correlation was 1. That means strong positive or perfect positive correlation. So if it's positive, because it's a positive number, correlation could be negative too. So this is perfect positive correlation. Okay. Now, on the other hand, think of the restaurant. What happens with the restaurant is this. If you spend $30, you may be giving $5 tip. If you spend $40, someone might give $10 tip. If you somebody spend $50, may end up giving $0 tip, or or $2 tip. Possible. Even though it is expected that you pay roughly about 15% in tips. This variable X and this variable Y has correlation. The more you spend, generally speaking, the more tips you pay. But there is no hard and fast rule. Like the way you worked extra hour, you got paid extra $15. There is a hard and fast rule there. There is a strict rule there. But here is more flexible. So the correlation, the strength of correlation here would be less than 1. Okay, unlike the last one, the strength of correlation here would be less than 1, because these numbers are variable, whereas in the last case, these numbers were not variable. Y was not variable. Y was very fixed. Like when you go to your local store, you buy something, let's say you pay taxes 8%. So if you spend $100, you have to pay $8 in taxes. You cannot say, oh no, I don't feel like paying $8 taxes today, I'll pay you $2 taxes. No, it doesn't work like that way. You have to pay exactly $8. On the other hand, if you go to restaurant, you're expected to pay $15 if you spend $100, but you may say, oh, I don't feel like giving $15. I may pay $5, or I may pay $30 in tips. So that number is variable. The Y, the second variable, is actually not as strongly correlated with the first variable, like the way taxes are correlated with the amount you spend. So that's another example. So this should give you different levels or different strength level in correlation. Okay, different levels or strength level or association level of correlation. Now, how do you measure correlation? Okay. Correlation is also known as Pearson linear correlation. This is called Pearson linear correlation coefficient R. Okay, R. This is defined as 1 over n minus 1 times summation x minus x bar divided by s sub x, y minus y bar divided by s sub y, and you sum it over all possible values. Now, the question is, this is a formula that you kind of have seen previously in an indirect way. Does it remind you of something? Anybody? Does this remind you of something? Particularly the arguments in front of the summation notation. Does it remind you of something?
It looks familiar, but I can't pinpoint it.
It looks familiar, but you can't pinpoint it?
Yeah, I was looking for my other notebook right now. I was like, where did I put it? Because I was like, it looks familiar, but I can't pinpoint it.
Okay. You wouldn't need to look for your notebook, but by the way, you will see it. You don't need to look for the notebook. It should kind of stick out like a sore thumb. Anybody else sees it? This kind of looks like x minus x bar divided by s, right? Doesn't it? Both of them?
Yes.
And what is that equal to? What is that equal to? Anybody? Let's see. Somebody made a comment. Yay! Thank you, George. Is this Zscore, isn't it?
He's correct.
Zscore. Yeah, this is Zscore, right? The other version of the Zscore is x, if you know the mu and sigma, x minus mu over sigma, right? If you don't know sigma and mu, then for sample, you can use this, right? X minus x bar over s. So this is Z-score. This is Z-score. Okay? That's what it is. It's the product of Z-scores. Now, remember, what does Z-score tell you? Z-score is important. It tells you the relative position of the data point with respect to the center or mean of the data point. It tells you relative position of the data point with respect to the mean or the center. Is this clear, everybody? So you are taking the relative position of x, each x, and multiplying it by the corresponding relative position of the y, and you're adding it up and dividing it by a constant, which is 1 over 1 n minus 1. Okay, so that's what it is. All right, great. So, and you can read it up. I didn't, for some reason, I didn't make the slides for this and this section, but you can read it up here. Main thing, one of the important things to remember, correlation doesn't imply causality, okay? And another kind of like terminology, bivariate data, that's kind of like XY pair, bivariate, okay? XY pair, that's what it means. Now let's go ahead and talk about some of the properties of Pearson linear correlation coefficient. Okay, first of all, these are the Pearson linear correlation. Okay, these are, it only measures linear relationship between two variables. It only measures linear relationship between two variables. What does it mean? It means like straight line, like this. That's a positive correlation, or negative correlation like this, like relationship that are linear in nature. I have given you one example of a few examples of positive correlation. Think of negative correlation. For instance, right now gas price is high, right? Gas price is high. If the gas prices go up, if gas prices go up, what happens to the number of miles you drive? It goes down. If gas prices go up, the number of miles you drive goes down. Okay, so which means that uh, this has a linear correlation. I'm assuming somewhat linear correlation, but if one goes up, the other goes down. So the relationship is going to be a negative correlation. Okay, one is positive correlation and one is negative correlation. In this case, the correlation is negative. Now, between two variables, you could have linear correlation or association that looks more like straight line. Like think of tips you pay and the amount of money you spend at a restaurant. It is a linear relationship, kind of. Generally speaking, the more you spend, the more tips you pay, right? Kind of like that. Okay. So that's what the linear relationship. However, between two variables, you could have non-linear relationship. So it's possible that some variables behave like this. Okay, two variables, they're related to each other, but they behave in a non-linear way. So remember that Pearson linear correlation coefficient, it does not measure the non-linear correlation. It does not measure the non-linear correlation. It only measures the linear correlation. That means straight line like correlation, not uh, something like curve, something like this. It won't measure that. So be clear on what you are measuring. Between two variables, you may have no linear correlation, but there may be a correlation which is non-linear. It's very important to keep in mind. You measure the correlation between two variables, but you find it to be almost non-existent. Okay, but there may be non-linear correlation. Okay, so next, Pearson linear correlation coefficient, the values range between -1 and +1. That means it's gonna be as low as -1 or as high as +1. Okay. Next, Pearson linear correlation coefficient of -1 means that it's perfectly negative correlation, whereas if R is 1, it's perfectly positive correlation. If R is 0, that means there is no linear correlation. Okay, there is no linear correlation, but keep in mind it indicates the absence of, so if R is equal to 0, indicates the absence of linear correlation, but there might be non-linear correlation. Okay, there might be non-linear correlation between the variables that we don't know about. Next, this is just a rule of thumb. If R, or linear correlation value, is greater than 0.8, it is considered a strong positive correlation. It may vary from subject to subject that you are studying. Or if you're studying biology, then it may be one type of correlation, strong correlation value you may use, one boundary. On the other hand, if you're in marketing, you may use a different one. But generally speaking, um, 0.8 or above is considered a strong positive correlation, and below negative 0.8 is considered strong negative correlation. But in reality, guys, if you're dealing with real data points, okay, in a study, it's unlikely that you'll get a correlation value of 0.8 or negative 0.8 or less, okay, or 0.8 or above. So it is very, very unlikely, very unlikely. Now, let's go ahead and talk about the next point, next characteristic of linear correlation coefficient. Pearson linear correlation coefficient are maybe significantly affected by the presence of outliers. So that means if you have an extreme data point in your data set, so it's recommended that you clear this data before you do correlation coefficient calculation. Example, let's say you go to a nice restaurant, let's say, and people pay nice tips, okay? Somebody spent $30, may give $10 tips. I'm making these numbers up. $50, and they pay $15 tip. $60, they pay $20 tips, or $70, pay $10 tips, okay? It doesn't have to be going up, by the way. Then there comes, let's say, a bunch of numbers, and then there comes somebody spent $150, okay, and gives $2,000 tips. Let's say those are the rest of the people are ordinary people, and this happens to be Elon Musk or Jeff Bezos or Bill Gates of the world, okay? Happens to be dropping by that restaurant, spent $150, and just happens to drop $2,000 tip. It's possible, not unlikely. I heard of a situation. There is a well-known guy in the tech industry. He's older now, but about 20 years ago, I heard that he went on a lunch and spent $15,000 on a lunch. I'm not going to tell the name because I'm recording it. So he spent $15,000 on a lunch. That's crazy. That was like back in 98, 99, 2000, around there. That's equivalent money. The way inflation has gone, this is probably more like $30,000 right now. So imagine spending $30,000 on a lunch. Anyway, so back to our point. So all the other data points are okay, but this data point is an extreme data point, which we also call outliers. You know that, right? This outlier. Now, if you increase this outlier in your data, in your correlation calculation, is going to significantly influence other data points or the correlation value, right? Is going to significantly influence, not increase, influence the correlation value. So it is a good idea to exclude data points like this before you do your correlation calculation. Okay, or there could be other extremes. Somebody stingy, spent $1,000 and gave $0 tip. Okay, so or could be even worse, paid $0 tips and wants discount on $1,000. Give me 10% discount, I'll pay $900. So possible. So extreme data points have to be excluded so that your correlation coefficient does not get impacted by that. Is this okay, everybody?
Yeah, so far.
Okay. Next, the value of R, the value of the Pearson correlation coefficient, is not affected by scaling. That means, let's say we are measuring the strength of relation or association between two variables, your height and your weight. In one case, we measure height in feet and weight in pounds. But then I decide to change feet to inches, okay, and keep the pound as it is. Just because I changed the unit of measurement for height, it should not be changing the linear correlation. Or if I keep the feet, but I instead of pounds, I use kilograms. Okay, that's the standard of unit in the rest of the world. For some reason, we still don't use the international system, which is not a very good thing. Okay, the rest of the world uses kilograms and liters, not pounds and gallons. I think US is the only country where we are using British system, and even the British, they don't use the system anymore. Pound, they went to um, international system, what is also known as MKS, I think, uh, meter, kilogram, and second. So anyway, just by changing the units, you do not change the correlation value at all. Why is it the case? Does anybody know? What if you change the units? It still doesn't change the correlation. Anybody? Nobody? Brittany, what do you think? Why does it not change the correlation, even if you change the units? George? George is not sure. Monica, what do you think?
Honestly, I am not sure why.
Anybody else? Okay. All right. Let me clean up the screen and take you back to the. Okay, George is saying something. Does the mean not change? The actual value of the mean will change if you change unit. Okay, so this is the reason that it doesn't change. In Pearson correlation coefficient formula, what you are using, not necessarily units, is the actual distance from the mean. This is the Z-score. Remember, I told you Z-score tells you how far off are you from the mean of a data set or the average of a data set, also known as the center of a data set. How far off are your data points? Okay, so you're not really using the unit so much in the calculation. You're rather using that distance from the average, distance from the center of the data points. Okay, so that's the reason. All right, next. So we have talked about these properties. So let me summarize again. Pearson correlation coefficient value must fall between -1 and +1. -1 means strong, perfect negative correlation. +1 means perfect positive correlation. If R correlation coefficient is greater than 0.8, is considered strong positive correlation. If R is less than -0.8, is considered strong negative correlation. The linear correlation coefficient may be significantly affected by the presence of outliers. So clear those data points before you do anything else, okay? The value of correlation coefficient is not affected by the data set. scaling of the data set. Scaling means you basically switch the unit or multiply by a constant, this or that. Okay. Any question about these 5 or 6 properties? No questions. Okay. Let's move on. Now, how do you actually find linear correlation between 2 variables? So I gave you 2 examples, okay? In the first one, I have XY pairs. XY pairs. X is the amount that a person spends. Y is the amount of tip that the person gives. So this is data, let's say, calculated from a restaurant. Somebody spent $20, get $3 tips, spent $10, get $0 tips. So the first number is X and the second number is Y. So X comma Y. This is also called bivariate data, okay? So, or pair, data pairs, okay? Pairs of data. This is one case. So there is a relationship between these XY variables. Similarly, there is a relationship between, here is the second problem, the number of hours student studies, okay, number of hours the student studies and his or her score in the exam, okay? So someone studies 5 hours, again, X comma Y, studies 5 hours and his or her score in the exam, 72. Studies 3 hours, gets 50. So first number is X, second number is Y. And somebody studies 13 hours, that's 95. So that's what it is. Now, I want you to go ahead and find this correlation coefficient. I know what these values are, but I'm not going to give it to you. I want you to find it. Correlation coefficient R. Everybody go online, okay? Search it on Google, and then you can find the correlation. And also I'll show you maybe later on how to exact command. I forgot the command. I think it's np.core, np.corr, okay? And then you give the values, okay? So you could use NumPy to find the correlation. Ideally, I'd like you to use this than anything else, okay? But for now, let's go ahead and go online and find just Google linear correlation coefficient or Google Pearson linear correlation coefficient calculator. Doesn't matter, you'll find lots of websites. So plug in the data points X and Y, it'll give you the actual value, okay?
And you want it for all the data points that are right here?
Yeah, you have to enter all of these data points. So you have to do 2 calculations. One is for this one, and another is for this one. One more thing before I tell you, the actually R gives you the relation, okay? Actually, we use R square as a sort of like square of the value, because R could be positive or negative. Square of the value as the strength of association, okay? How strongly they are associated. So go ahead and find the R for first set of data, R for second set of data. I'll give you a few minutes to work on it, okay? Okay, I am looking at your chat messages and I see that people got the right values, okay? So R for the first case is 0.96, okay, approximately. And R for the second case is 0.86, okay? R for the first case is 0.96, R for the second case is 0.86. So this kind of gives you the idea of linear correlation or association between these 2 variables. Okay. Now now that you know how to do it, I'll basically tell you that I'll give you some simple problems in the homework as well as in the final, where you'll be doing calculation for correlation and use that calculation to do the next thing, which I'm going to be talking about, using linear correlation. Okay, using linear correlation to do hypothesis testing. I took the exact same two problems and I added something to it, which you will see. And I will do both of these problems for you. It's pretty easy, straightforward. So let's go ahead and do it. So now we talked about linear correlation. Now we need to talk about hypothesis testing using linear correlation coefficient, okay? How do you do it? Again, the same standard type of process that we have followed. You want to find out whether there is a linear correlation between two variables. Let's call them X and Y, okay? Between two variables, is there a linear correlation? Now, the way you do it is this, by following these steps. First, you kind of ensure that in the data set, you do not have any extreme data points or outliers. Remember, I told you, if you have extreme data points or outliers, that is, or that are going to influence the linear correlation coefficient value. So you want to exclude those data points to have a more of a sensible and consistent data set. So that's the first thing you do. Second thing is your null hypothesis is rho is equal to 0. This is rho. This is not P. It kind of looks like this. Rho is spelled R-H-O, rho. Okay? So rho is equal to 0 means there is no linear correlation. Okay? Means there is no linear correlation. Rho is the population correlation, the correlation between these two populations, okay? And on the other hand, rho is not equal to 0. Rho is not equal to 0, meaning that there is some correlation between these two variables. So this is your null hypothesis, and this is your alternative hypothesis. Your test statistic, which technically should be R star, that's the convention that I have been using. R star is your test statistic, is nothing but the linear correlation coefficient value that you got, or correlation coefficient value that you get by using the data that you have been provided. And in the next step, you find the critical values and regions, right? Remember how in the normal distribution case, using the central limit theorem, we found the critical regions from here to here, okay? If it's to the left or to the right, or if we do one tail test, this left side, let's say left tail, right side, right tail, or both tail, we found the critical regions, right? Again, we have a critical region, but rather a critical value in the case of correlation. And next, you make your conclusion based on the absolute value of the correlation. Remember, correlation could be negative, right? So you take the absolute value of the correlation and you compare that value with the critical value that you get in the last step. If this R, absolute value of R, is greater than that, let's say R sub C, critical value, okay, then you reject the null hypothesis. What is the null hypothesis? That there is no linear correlation. Rho is equal to 0, means no linear correlation. On the other hand, if your absolute value of R is less than that critical value, then you do not reject the null hypothesis H sub 0, which says rho is equal to 0. Rho equal to 0 means no correlation, no linear correlation. Rho is equal to 0 means no linear correlation. Now, these are the steps that you're going to go through, okay? Very straightforward, very simple, nothing complicated. Is this clear to everybody? Any questions on this, anyone? Okay. There is one question from Dennis. Could 200, 40 be considered an outlier? No. See, what we are comparing is the restaurant tip, I think. Where is 240? Okay, so look at this data point. Is that, yeah, it's a outlier in the sense it's a big amount, but it's consistent, okay, with other data points. If somebody spent $200 and gave $2,000 tips, okay, then that might be considered an outlier. So I don't consider this as an outlier, okay. I could keep it, okay. But again, remember, these things are a bit subjective. Someone might say, okay, 200 is a big number in terms of having a lunch or having a dinner, so I may consider it an outlier, but I probably wouldn't. Okay. Let's go ahead and do the hypothesis testing. Exactly the same thing that you did. These are the same numbers for which you found the correlation. So we are gonna first look at this data set. Is there anything looks obviously an outlier? The answer is no. So we are okay on that part. No outliers. Your null hypothesis is going to be rho is equal to 0. That means there is no linear correlation. On the other hand, your alternative hypothesis is rho is not equal to 0. That means there is probably some kind of linear correlation. And your test statistic, I put R star here, but I forgot to put R star here, is 0.96. This is the only value that you would calculate. The test statistic is R star. Now, here degrees of freedom is n minus 2, not n minus 1. Okay, now where do you look at? Everybody open the table, okay? Open the table and go to page number 3, okay? Go to page number 3. Okay. And then you can see the Pearson correlation coefficient values for different alphas. So for up, you have degrees of freedom n, then alpha is equal to 0.05, and then alpha is equal to 0.01. And you have values like this. So degrees of freedom, go down the degrees of freedom and look for 8, because we have 10 pairs of data. So degrees of freedom is 10 minus 2, 8. And look here, what value is it? And that value, give it to me, everybody. Look at it quickly. Look at the table, page number 3, and you'll see correlation coefficient table. 0.707. I have it here too, right? 0.707. Good. That is the value. Now, your R star, absolute value of R star, technically, absolute value of that is 0.96, which is greater than 0.707. Therefore, you reject the null hypothesis, reject the H naught, that rho is equal to 0. On the other hand, let's say hypothetically speaking, if your absolute value of R star were, let's say 0.5, in that case, that would be less than 0.707, then you do not reject H naught, which is rho is equal to 0. That's the way to go. Now, I want you to do one more step here, which is this. What about alpha is equal to 0.01? Do we reject H naught for alpha is equal to 0.01? If we go from 0.05, which is the which is the significance level, we change it to 0.01 significance level, then we will have this value, whatever that value is, I don't know. Can you find that value and compare it against this to reject or not to reject the null hypothesis at 0.01 significance level? At 0.01 significance level, would you reject the null hypothesis or you wouldn't? Can you find that value and help me out, please? Thank you, Monica and George, both. So the value is 0.834. Your R value at this point, at this location, 0.834. R value is 0.834, which is still less than 0.96, right? So 0.96 is 0.96 is still greater than 0.834. That means you would still reject the null hypothesis. You'd still reject this at 0.01 significance level. Remember, 0.01 significance means 1%, right? 0.01 significance level means your confidence level is 100% minus 1%, or 1 minus 0.01, or 99% confidence level. Your significance level is 0.01, means 99% confidence level. Okay, the same thing. Similarly, rather, your significance level is 0.05 right here, means you have 95% confidence level in your calculation. All right, so any question on this process, everybody?
No.
Everybody okay?
I just need to practice it a little bit.
Okay, you will get it right now, Don. Let's do the same thing for this problem. So go ahead and practice it. I'll give you a few minutes. Do the exact same process that I did, and then make a conclusion whether you'd reject the null hypothesis or you would not. Everybody, please go ahead. So there are 5 steps or so in doing the hypothesis testing here. So step number 1. Step number 1, are there any outliers in this data set? In this context, it could be somebody started 20 hours and got maybe 20 in the exams, something like that. Probably no, right? So outliers, no. Number 2, your null hypothesis is rho is equal to 0. That means there is no linear correlation, versus there is linear correlation, which is rho is not equal to 0. Step number 3, your test statistic R star, which is 0.86, isn't it? That's what you got. Now, step number 4, your critical values for R, which happens to be also 707, because your degrees of freedom is n minus 2. We have 10 pairs of data, 10 minus 2, which is 8. And alpha happens to be also 0.05, the same alpha as the last one. So that's also the same. Step number 5, absolute value of R star is absolute value of 0.86, which is 0.86, right? Obviously, that is greater than 0.707. So based on this, okay, we reject the null hypothesis that rho is equal to 0. We reject the null hypothesis that rho is equal to 0. Is this clear, everybody?
Yeah, now it makes sense. I got to see the steps all together.
Yeah, that's clear.
It just takes a little bit of time. It's like everything else in life. You just have to see it a few times. Okay. The more important thing is to like have fun with it. Just try it, have fun with it, do it multiple times, you'll get it. It's not as bad.
Is there a reason why P equals 0.707? Is it because the N
P
equals 8? Is that why?
Not
the,
P, you mean R.
R, my bad. Why is that equal 0.7? Is it? I never got that.
0.707, this value comes from the table. On the third page of the table that I gave you,
Yeah.
You look it up there, you have 3 columns. One is degrees of freedom, one is alpha is equal to 0.05, and the other one is alpha is equal to 0.01. Now, if you go down the degrees of freedom, there will be a row labeled 8, which is the degrees of freedom 8.
Oh, I got so
here.
confused because I thought we had to like calculate something else, and I was like, okay, then this is gonna be the answer, but I didn't find 0.707. Like, oh, what's going on? Okay, I understand now. That's good to know. Thank you.
And also at 0.01 significance level, would you reject it? What was the value? 0.83? Was it 0.831 or 83 something?
It's 0.834.
0.834. Still, you'd reject it because 0.86 is greater than 0.83, right? So you'd still reject the null hypothesis that there is no linear correlation between these two variables. Is this okay, guys? Does it make sense to you?
Yeah, it makes sorry, excuse me. It makes a lot more sense now. It's actually, yeah.
Any other questions, anybody?
I don't have any.
All right. If not, that's all for the day. Excuse me. That's all for the day. And we will meet on Wednesday. Thank you very much, you guys.